SwayamPrabha. Digital India. Educated India.
Now, this is the one example I am trying to tell you. Again, you do not have to worry about few things. Let me get it very clear. You should not be worrying about this drawing. Okay? These are the protein backbone. Protein backbone means amino acid put together, it is forming. It's a huge polymer. Polymer means, let's say, it's a huge length. It could be a lot of things together, lot of amino acid together. And that's how these sort of different orientations are given, because that's how they look like. Different way of their structural aspects that's going on over here, structure are different. So you do not have to worry about all these protein backbone or the peptide backbone. If you zoom on over here, you see that amino acid backbone. These are from different amino acid. All those amino acid, if you look at, you can see their structure. They are nothing but organic compound. Okay? For example, over here, tyrosine. Tyrosine is nothing but phenol containing amino acid which has a phenol, let's say, phenol. Tyrosine oxygen can bind with the iron center. Another tyrosine oxygen phenyl ring, phenol, oxygen can bind with the iron center. This is histidine. And this is aspartate. Aspartate is having carboxylic acid, CO2H, carboxylic acid. That can bind with the iron center. This is having histidine unit, okay, just nothing but imidazole. Imidazole you have heard of? Imidazole, phenol, carboxylic acid. These are the side chain of amino acid. All those amino acid we know, which it is having some side chain which can bind with the iron center or any other metal center. So this is the one, let's say it's transport iron. That's what I was telling. This is a pizza delivery guy. It's a delivery guy, iron delivery guy, right? Now it picks up iron from different site, and it essentially, see, it's not like they have to move, they can just pass on also. I can give, it can be a relay process as well, right? Overall, this is where it picks up, or that's how one of the example we are showing, how the metal center is going to be picked up. It binds with the amino acid backbone and it gets picked up and then delivered at a certain point where it can be stored. Pick up iron from storage iron protein. Okay, you can read, but usually what we see is iron centers during this movement, when it is moving, this is pick up and delivery time, it is going to be +2. During transport and storage, it is stabilized in +3 state, because +3 are the one which is oxidized state, little bit stable state. During this storage, it has to be stable. So their redox chemistry is used for their transport as well, right? Storing is in +3 form, and during transport also it's in +3 form. During picking up and during delivery, it is in +2 form. Okay? All right. So what essentially we are trying to tell you is a metal ion gets delivered by different approach. One of the main approach is simply different protein backbone, that is nothing but amino acid backbone. Protein backbone is nothing but amino acid backbone. Amino acid has this phenol unit, this imidazole unit, carboxylic acid unit. These are ligand. These usually acts as a monodentate ligand and thereby can bind with either, let's say, iron 2+ or iron 3+ or zinc 2+ or copper 1+, copper 2+. Okay. Of course, you have to also understand that hard soft, I told you, hard soft acid base. When you have a harder one, for example, so harder anion will come, right? When you have, let's say, you have copper 1 plus versus copper 2 plus. Copper 2 plus is harder one. So if copper 2 plus has to be delivered, and let's say the ligands are very hard, copper 2 plus is hard, so the ligands associated with it during the delivery time, it's, let's say, very hard, right? Hard anions are bound. Now the place where it is going to get delivered, it is not having the harder anion. What copper has to do, or copper has to undergo, is reduction. Copper 2 plus will undergo reduction to come to copper 1 plus. Since copper 1 plus is soft, that site previously which was having hard ligand, it will not bind it very tightly. Now that softer copper 1 can be exchanged from one place to another. Let's say storage place, if you say, or the delivery place, wherever it is delivering. So that's how things gets also delivered. You have very hard situation, very strong situation, hard anion, all the oxides, let's say, are bound. Let's say carboxylate, O minus, or phenolate, pH O minus. Different, whatever you know as hard ligands are bound with a hard cation. Now then you want to deliver it to a softer place. So the metal center has to undergo a reduction, and thereby softer center will pick it up, and the reverse is true also the other case, soft to going to hard. So all this simple principle actually matters. What ligands is there, what ligand environment is there, what oxidation state is there, and thereby you can deliver in a particular manner. So this is another enzyme I am just giving. Again, you do not try to memorize too much, because you may not be able to get into too much detail. We don't want you also at this point. These are protein backbone. It looks quite funky and big, but if you nail it down, if you zoom it down, what you see is this. So different protein backbone is coordinated with metal center, and another different protein backbone is coordinated with another center. Essentially, once again, hard, soft, acid base principle will be followed. Of course, also another thing you have to see, what is available. Sometimes whatever is available, they can still go with it. If there is no competition between hard and soft center, even if it is in a soft center, hard, if metal center is soft, but hard anions are the one which is available, it's okay, it will go with it. It's not like they cannot bind. Binding efficiency may not be great. That's it. Overall, I think what we are trying to say is, this enzyme is able to function since copper can undergo oxidation state, blah, blah, blah. You read it. I think I explained it. Copper 1 plus and copper 2 plus, iron 2 plus and iron 3 plus, these oxidation state change help you to do a lot of chemistry. 1 or 2 chemistry we will discuss today. That is number 1. Now, zinc plus doesn't undergo usually this oxidation state change. They can give the structural aspect. They hold things together and thereby provide some chemistry to be done at that center. Let's move on. Now, I think the major part of the syllabus is on hemoglobin and myoglobin, or so-called the porphyrin centers. Right. I don't know whether you have studied little bit before. Okay, fine. So porphyrin center is something, this is one thing I would ask you to remember and draw it again and again. Usually what people do is, they cannot provide this double bond in a rational manner. You try to draw it, usually in the exam it is given. Okay, draw porphyrin, or you will be asking a question in a way that you have to draw porphyrin. Okay, draw the porphyrin. What is not important is these R, what substituents are there. Of course, these substituents, these R group, will determine whether a complex is going to be soluble or how soluble. They have a role, okay? But for this class, you do not have to understand or know what the role they are actually playing. By changing the R group, you can change or modulate the properties to some extent. Okay? Now, this is the porphyrin you should be very familiar with. This is nothing but a ligand. This is a chelator. It chelates the metal center. Actually, it's a tetradentate ligand. Usually what we have seen so far in the amino acid backbone is monodentate ligand, usually, right? Means only one coordination sites are there. One, let's say phenol oxygen can bind, right? Imidazole nitrogen can bind. But porphyrin, these 1, 2, 3, 4 nitrogen can bind, and if you put a metal center over there, you can see 1, 2, 3, 4, 5, 6. 6-membered metal, that ring will be formed. You have seen the bidentate ligand, how they are forming, how they are biting it, bidentate, they are biting it. This is like tetradentate, and this is a very good chelate. It can, it's almost like those EDTA we were talking. EDTA can extract out. Porphyrin is a strong ligand. It can extract out iron, let's say, or any metal center very easily. Okay? Not, of course, not neutral form. Let's say iron 2+ or iron 3+. These can be extracted, or these can be put very easily over here. Of course, there is a size, right? There is a cavity. So anything that doesn't fit into that cavity will not have strong binding with the porphyrin. So the size of the iron, let's say iron 2+ versus iron 3+, will matter whether it can fit in here or not properly. Okay? High spin and low spin will matter, and thereby, of course, high spin, low spin size will be different, right? And thereby you can see whether metal can be sitting over there or not. Okay? Now this is what I was talking about, iron binding. You see 6-membered ring, 6-membered ring, 6-membered ring, and 6-membered ring. It's holding it very tightly. You do not have to memorize this side chain. You have to just remember the core structure. Core structure includes this pyrrole ring, right? So these side chain, whether this is a double bond or a methyl, double bond or methyl or carboxylic acid, these are the one you do not have to remember anything. Okay? But the porphyrin ring itself, porphyrin ring means without those substituent. That's the simple porphyrin. Okay? You can then substitute. So you should be very familiar with this. This is the imidazole, which also binds at the, so if porphyrin is actually flat, like this flat, so iron is right, let's say, in the middle of my palm, and then imidazole is right over here in the middle. So below this plane, this is a plane, below this plane imidazole is bound like that. Okay? So it's a tetradentate ligand. Porphyrin is a tetradentate ligand. This is the 5th coordination, imidazole. Okay? The 6th coordination is over here, which is open, or almost, let's say, something is there very far, interacting, not too close. This is the center where oxygen binds. When we are inhaling, right, oxygen gets in, this is the site on top of it, on top of the flat porphyrin ring that binds the oxygen, and that determines the life. You can now imagine, I will come to that, if this oxygen binding site, this is imidazole, this is oxygen binding site. If this oxygen binding site is occupied by carbon monoxide or cyanide, okay, I will see you again after life. Okay. So that's what happens. Those bindings are going to be stronger, right? Compared to oxygen binding, those bindings are very strong. So oxygen cannot displace them. The ligand exchange between oxygen and CO will not happen. or cyanide will not happen. Other way around may happen. Oxygen can go off, cyanide can come in. That is why it becomes so poisonous, so deadly. Carbon monoxide, cyano, and so on. It is also one of your tutorial question. Okay? Now, I will go into again, once again, do not get, I mean, sometimes we do get very, well, there is feedback also, right? Please give your feedback, not at the end of the class. Usually, I think at the end of the semester or something, you are allowed to evaluate us as a teacher. The way we do also get an opportunity to evaluate your performance by taking exam. I think that is kind of our exam. It determines a lot of things for us. So take it seriously for all of you or for all of the teachers, because it determines, of course, not too serious. It's not life threatening, but it determines something. Okay. Okay. So one of the major objective or topic of this chapter is myoglobin and hemoglobin. How molecular oxygen or oxygen, which is in the air, how it binds in the blood. In the blood we have porphyrin center. The porphyrin center we were discussing over here, right? So this is there in the blood, and how oxygen from air binds with this center, and what happens during this binding. What happens when oxygen gets released? Okay? So as you know, usually what we have learned or what happens, oxygen goes in for our body. We are showing just human. It goes in the lungs, it gets in, and then it gets delivered from all body parts, right? Now let's say in the muscles it gets stored, right? It gets stored in muscle. So how oxygen is going to get transported, and then how it is get stored in the muscle? That is the one kind of the major things we will be discussing today. So the storage protein, let's say in muscle, what we have is myoglobin, where that's what we are trying to say. Iron storage is there, some other metal storage is there, then oxygen storage is there, oxygen transport is there, right? So hemoglobin is the one which transports oxygen. Myoglobin is a single unit, means one porphyrin center is there, only one. Hemoglobin is the one where 4 units are there, 4 iron centers are there, 4 porphyrins are there. Okay? Where are they? Roughly, again, you do not have to even attempt to memorize any of this structure. Please do not. Okay? This is a heme center, this is another heme center, this is another heme center, this is another heme center. Heme means porphyrin ring plus iron. That's called heme. That porphyrin ring flat plus iron. That's the heme. So we have a heme center in here. We have 4 heme centers are in there. How they are connected? They are connected by this protein backbone. Okay? It could be, let's say, I mean, heme center is here, another heme center is here. In between, heme center is there, another heme center is there. In between, there is those protein backbone, amino acid side chain. Lots of amino acid side chain putting together, of course, is peptide backbone. Those protein backbone, peptide put together is forming protein. Those protein backbones are together. It's not like all of them has to be covalently linked. Covalent bond we know. Some of them are covalent bond, some of them are just linked by hydrogen bonding. Let's say this is a protein, this is another protein, they are linked by hydrogen bonding, right? So heme center, they are linked by, let's say, simply said amino acid residue, which is having, let's say, your covalent bonding. Okay? So all of them are connected, if not directly, none of them are directly connected. Like iron center bound with nitrogen, that's a direct coordination. Okay? But there is indirect coordination such as hydrogen bonding and other loose forces, okay, which becomes important. So they are connected, they can communicate with each other, they can talk. It's just like we can communicate, they can communicate with each other. That is essential. Okay. Communicate means what happens to this center. When something happens to this center comes to know. If something happens to this center comes to know, and it relays. That is, that relay of information we will be learning in form of cooperativity. They cooperate with each other. Okay? That's the cooperativity. That thing is missing from myoglobin because they have no one to communicate. They are isolated kind of system. One porphyrin center. It's not like they are unhappy, just they don't want to communicate. Okay. Now, of course, if you want to compare hemoglobin and myoglobin, first thing I said is this is the myoglobin 1, hemoglobin 1 having 4 iron center, so 4 unit versus 1 unit. Okay. Of course, their molecular weight is going to be related by 4 times. So hemoglobin is approximately 4 times compared to myoglobin. Okay. Of course, both of them are having porphyrin. Both of them are red in color in the oxyform. What is oxyform? Oxyform simply means that oxygen is bound. Deoxyform means that oxygen is not bound, period. Okay. Oxyhemoglobin, deoxyhemoglobin. Oxymyoglobin, deoxymyoglobin. These terms will be used. Deoxy means no oxygen is there. Okay. Yeah. What is there to remember? I don't see anything to remember. It's this. What I am saying, you remember this, nothing to remember. This is a porphyrin center, iron is there, porphyrin you have to remember, yes, porphyrin you have to remember. That's the only thing I am asking you to remember. Rest of the things you can just read or understand as a story. I think that's good enough. Story we do remember, I guess. We can tell a tale, right? Now, okay, so the color, as you know, the blood color is red. It's simple, right? It's going to be red. Now, deoxyform, if you do not have any oxygen in it, it's going to be red purple. Okay, if you don't want to remember, don't remember. Okay, now, okay, I didn't mean in that way. Okay, of course, iron is in reduced form. You are going to add oxygen, okay, so iron will be in reduced form. Okay, what we will not be discussing today is the redox chemistry. What happens to the iron? Is it going to iron 3 plus? Yes, it goes, but that information we will not be discussing for the class. What we will discuss is initially what happens. Initially redox chemistry doesn't happen. Redox chemistry happens right after it. We don't need to know this. We will discuss that oxygen comes and binds with iron center. That's it. That's the syllabus. Right after that binding, oxygen actually gets reduced, iron gets oxidized. That is not part of the syllabus, don't even write in the exam. Okay? I will be discussing whatever part in the syllabus. Okay, this is the same thing again. 1, 2, 3, 4 iron center, nothing else. Okay? 1, 2, 3, 4 iron center. We are discussing myoglobin? No. Hemoglobin. See, you understand by now. Okay. Now, see, something like if you put a lot of oxygen in a lot of oxygen, or other way around, if lot of oxygen is not there, you will be suffocating, right? You feel breathless, that means oxygen is not there. Breathless situation is less oxygen, right? That situation, and then if you compare to breathless situation, if you want to pressurize oxygen, too much oxygen is there. That oxygen pressure you can vary. And then you can measure how oxygen is uptake. Uptake means how it is taking. How porphyrin center in hemoglobin and myoglobin is taking up oxygen with respect to oxygen pressure. You pressurize oxygen, say gas cylinder, let's say. You can pressurize gas cylinder, you can have not so pressurized gas cylinder. With respect to partial pressure of oxygen, as you increasing the pressure of oxygen, and you see how oxygen pickup is happening at the myoglobin and hemoglobin. What do? This is the curve for hemoglobin. Okay? This is the curve for myoglobin. And this is the curve for hemoglobin at pH 7.6. Hemoglobin pH 6.8 is red curve. A lot of things are red. This one, sigmoidal curve, is at pH 6.8 hemoglobin. pH 7.6 is the blue curve for hemoglobin. And then myoglobin, that's the curve. Now, so what we are seeing, as you increase the partial pressure of oxygen, oxygen uptake goes up. Percentage saturation means you can keep on bind the iron center. You have more oxygen pressure, it will go up, the curve, sigmoidal curve you are saying, it will go up, and after certain point it will saturate. It will not take up any more oxygen. That means that's the maximum, that's almost like the equilibrium is reached. Okay? After that no more oxygen pickup will happen. So you pressure, you take pure oxygen, we have 16% oxygen, pure oxygen you can take, or pressurized oxygen you can take. So therefore what we have measured here is oxygen pressure is going up, how saturation level is going, how our hemoglobin and myoglobin is uptaking. Now in lungs, what happens? In lungs we have, this is the partial pressure. Now it's almost it's very, very high oxygen amount we can take it up. Okay? Where at the low pressure, if you see, okay, at the low pressure you see the myoglobin is having higher affinity. That's in the muscles where low pressure of oxygen is there. Oxygen is going to transfer from hemoglobin to myoglobin in muscles. Because, firstly because at a low pressure of, myoglobin has a higher affinity or higher affinity for oxygen compared to hemoglobin. Okay? And myoglobin also has pH something like 6.8 at a lower pH. So at a lower pH, this is the pH curve. With respect to pH, hemoglobin oxygen uptake is shown in here. At higher pH, oxygen uptake is shown in there. Since in muscles pH is low, then what happens from hemoglobin? So hemoglobin is over here, that much oxygen it can pick up. Myoglobin right over there is having high affinity for oxygen. Therefore, hemoglobin to myoglobin transfer will happen. Okay? That's how the transfer mainly happens. Both at a lower pressure, myoglobin has higher binding, and the pH for pH 6.8, this is pH 6.8 curve, you see hemoglobin binding is over here, myoglobin binding is over there. And therefore, hemoglobin to myoglobin oxygen transfer occurs. Okay, it's very beautifully written in this here. You can read, it's a Stiver-Atkins book, which is your textbook. You can read in there in detail. Now let's go on. So what is essential for oxygen binding? Irrespective of myoglobin and hemoglobin, what is essential? The thing that is most essential is we have to prevent reduction of oxygen. Oxygen can get reduced by 2 electron, that is oxygen to peroxo formation can happen. Iron center can give 1 electron, another electron, the second electron can also come from either that iron center or from another iron center. Since you are seeing that 2 iron centers are really far apart from each other, okay, although they communicate, but the electron transfer will not be that very fast. Okay. So, therefore, what happens is oxygen to peroxo formation does not happen. That would have been a irreversible thing. So, what all happens in our body is a reversible oxygen binding. Oxygen does not get reduced completely to peroxide, hydrogen peroxide, let us say, that reduction does not happen fully. Oxygen to peroxide level reduction is prevented by default, by design, okay, because the 2 electrons are required, oxygen to peroxo. That 2 electron reduction cannot be possible because that reducing equivalent means that you need something to give electron, right. That is how you will reduce. Reducing equivalent is not available readily. There is nothing to reduce very readily right over there. That is one aspect. Another aspect is of course you have to prevent the oxygen from going out. It has to bind. Those binding, even though it is not that very strong, what happens over here is, let us say it binds over here, for example, oxygen is over here, this oxygen will have, after binding, oxygen will have hydrogen bonding, some sort of, so let us say this is my porphyrin, this is my iron center, oxygen binds this lone pair, right, and this is the axial position top. The below is again your histidine or histidine unit, right. This is your porphyrin. Now, this oxygen you will see there is a hydrogen bonding from another histidine. So, this hydrogen bonding also gives the stability to the structure. Okay. Overall, it is a bent oxygen geometry and it prevents the reduction oxygen to peroxide. This is peroxide reduction. That is what happens in our body. When you try to synthesize porphyrin, which I have done, let us say, actually I have done, if you take porphyrin and iron synthetically prepared. So, that is why synthetic blood is very difficult to prepare. Why? Because the moment you have porphyrin, okay, it reacts with oxygen. If you have porphyrin synthetically made, it reacts with oxygen. Overall, what you get is here iron 3. See, what happens here is porphyrin is too far. Oxygen can come over here. It cannot bridge between 2 porphyrin. But in synthetic system, 2 porphyrin can come very close because there is no restriction. There is your globular protein. That is again another tutorial question, which is preventing the dimerization and also providing the stability for the monomeric structure. In synthetic system, what is happening is, or what can happen invariably, 99.99% cases, it happens that porphyrin, P means porphyrin, oxygen reacts, and overall you do not have to remember all these again. This one, iron 3, each iron is giving 1 electron, therefore iron 2 plus going to iron 3 plus, oxygen is getting reduced by 2 units, oxygen to peroxide forming. This reaction is killing the porphyrin or the oxygen binding. This is not too much of a reversible reaction. So in our body, what happens is it's a reversible oxygen binding. Oxygen can bind and pop up. It can go. It can be delivered to myoglobin. Hemoglobin takes up, transport and deliver. In synthetic system, it is very, very rare to deliver. How you can deliver? That can be done in synthetic system. It requires, if you put some steric bulk means, let's say you put an umbrella. You put an umbrella on top of porphyrin. Of course, that will take a lot of synthetic effort to put an umbrella on porphyrin. If you put an umbrella, another umbrella will not be able to come very close and affect. So another umbrella, even if it comes, it will come over here, but iron site is here, iron site is here. So they too cannot communicate. So these are called steric effect. You put bulk and thereby you prevent, but that is very, very expensive. I mean, it's a lot of synthetic effort. But by default, nature has it. In our body, we do have that by default. We do have what? We do have this protein backbone. Protein backbone prevent these two porphyrin to come close, and thereby we do not have any problem to deal with, right?